Welcome to this lesson. In this lesson, we are going to be looking at applications of systems of linear equations. And I know that's a mouthful. What that means is we're going to be looking at word problems or real-life situations that lead us to systems of linear equations. So basically what's going to happen here is we're going to be given some sort of word problem. You're going to write that as a system of linear equations. You're going to solve the system of linear equations and figure out if that answers the problem that you're being asked or solves it. So in order to do this, then I want to go over our steps for solving all word problems. So we've gone over this before in this course, but I just want to reiterate what those steps are. That there's 4 steps to solving any word problem you ever see, any application problem. Those 4 steps are understand, translate, solve, and interpret. So let's go over those steps in a little more detail. In the understand step, this is where you're going to read the problem, you're going to draw any pictures that might apply so that you can kind of understand and visualize what's going on. If there's a formula that applies, you can write that down as well. And the other part that I've talked about before that I just want to really reiterate is define your variables in words. Don't just say X. In words, you want to say X is representing blah, 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 whatever it's representing. This is extremely important in this particular lesson more than any other. And the reason being that you're always going to have at least 2 different variables. Oftentimes in these problems, you're going to be asked a specific question. Sometimes that question is the answer to that question is going to be X. Sometimes it's Y. Sometimes it's neither. Sometimes you got to do something to your X or your Y to get to your final answer. So it's really important to define our variables in words so that later on in the problem we can say, did I actually solve what I was even being asked to solve? What is it that my answer is? So these are important things to be aware of, so we have to define those variables in words. And again, because we're having multiple variables here. So we need to make sure we understand what our variables are representing. I can't stress that enough. Step 2, translate. So translate's where we take the words that are on paper and put it into an equation. And these are skills that you've built up before with keywords, with translating words, and different strategies. And we'll go through what some of those strategies are as we look at example problems. Step 3 is solve. This is where you basically have a homework problem in front of you and you just solve it and get an answer. So this isn't tricky in terms of it being a word problem, except for the fact that sometimes the numbers don't work out quite as nicely as a homework problem. We're going to get more decimal answers because we're talking about real life numbers here. But otherwise, it's just solving a normal old homework problem. Now, step 4 is super important. This is where a lot of people misstep, and it's where understand step helps you a ton. The 4th step is interpret, to interpret the answer that you came up with. So as I was saying earlier, sometimes when we solve a system and we get an X and a Y, that doesn't answer the question that was actually asked of us. Sometimes you're only asked one question, and so maybe the answer to that question is the value of X. Sometimes it might be the value of Y. Sometimes it might be the sum of those. Maybe it's something completely different that you have to use those values to find. So in our interpret step, we're going to reread what the question's actually asking in the first place. Then we're going to look back at how we defined our variables and say, did I answer it? Can I answer the question with the information that I've used, that I've solved? And then the next important thing to ask is, does my answer make sense? Because maybe I made a mistake. Or maybe I didn't write down my understand step well enough, and so I'm giving the wrong variable. So if you're asked for instance, a mortgage payment on a $300,000 house, and your answer is $50, your answer's wrong. So you got to look at that and say, hey, could I really pay $50 a month and have a $300,000 house? Probably not. Not unless you have a really big down payment, like $250,000 down payment. So we got to look and say, does that make sense? If you're calculating the speed of the wind, which is something that we will be doing in this lesson, and you get an answer like 150 miles an hour, well, you're probably not going to have 150 mile an hour wind. You're talking like really ridiculous hurricane winds there. So when you get answers like that, that's ridiculous. If you're calculating the speed that somebody jogs at and you're calculating 50 miles an hour, you can't jog 50 miles an hour. So you got to think about your answer and say, does that make sense? If you're calculating how much paint it takes to paint a room, and you come up with an answer of 5,000 gallons, are you really going to go into Home Depot and load up a cart with 5,000 gallons of paint for one bedroom? You're going to fill the bedroom with just your paint cans. It's not going to make sense. So think about your answers and say, does this make sense? All right. So with that overview, let's talk about what types of problems we will be solving here. So we're going to start off with some very simple, straightforward problems in which we just translate two equations and get an answer just to get some practice in the translating. We're then going to go back and look at some of the stuff that you did in Math 53 or a prerequisite math course and see how we can use some of these strategies to solve problems that you may have solved before. We're then going to look at some new things that you might not have seen before, like problems that involve wind and current and how that might affect. So a wind and how it affects a plane that's flying, or a current and how that affects a boat that's trying to travel in the water. So we're going to look at things along those lines. Then we're going to look at problems that result in three equations with three unknowns. And so that's pretty much the structure of what we're going to go through in this lesson. Now, as we read through this example, we see that we have a total of 100 coins that all come from being dimes and quarters, and their value is 1150. And our goal is to find the number of each type of coin. Now, a lot of times in these word problems, the first thing that you're going to be doing is defining what your variables are. And this is really, really, really important to define what your variables are. So we're going to define them in words. Now, if you're having a hard time deciding what your variables should be, a good place to look is the question itself. The question itself is often going to say, hey, find this for me. We're asked to find the number of each type of coin. So we're asked the number of dimes, the number of quarters. So that's a great thing to define as our variable. So let's define D as the number of dimes, and let's define Q as the number of quarters. Now, we have to come up with two equations now somehow. So as we read back through here, we're told two different pieces of information. One about the number of coins that we have, and one about the value of the coins. So these are going to lead to our two equations. Now, how we define our variables is really important now. So we've got to come back to the fact that our variables are representing number of coins, the D for the number of dimes and Q for the number of quarters. So as far as the equations are concerned, that's going to dictate how we write them. So the first equation says we have a total of 100 coins. So that means if I add together my number of dimes and my number of quarters, that should be 100. But then the other piece of information is about the total value. So the value of the coins is 1150. So in this case, don't write this down. We're not simply going to say if I add D plus Q, because D plus Q is not talking about the value from the dimes or the value from the quarters. So I have to consider the fact that dimes are worth 10 cents. So for every dime I have, I'm going to multiply by 10 cents. Or another way of saying that is 0.10 times the number of dimes. That's the value that I have from dimes. The value that I have from quarters would be 0.25 times the number of quarters that I have. Now, if I add those two values together, that's where I should get 1150. Now, if you want, you could go ahead and clear your decimals, kind of like how we clear fractions. So you could multiply both sides of the equation by 100 in order to remove the decimal point, or we could just deal with them. It's up to you, doesn't really matter. Now that we have our system of linear equations, we now need to solve this. And we can use either substitution or addition, doesn't really matter. I'd probably actually use substitution on this one. I would look at that first equation and say, I can solve for D pretty darn easily as 100 minus Q. I could then take that and plug it into the second equation, and I'm going to get 0.10. Now instead of D, I'm going to have 100 minus Q plus my 0.25 Q equals 1150. Now if I distribute my 0.10 across, I'm going to get 10 minus 0.10Q plus 0.25Q equals 1150. Now we can combine like terms with our Q's. 25 minus 10 gives us 15, or 0.15Q. And we can go ahead and subtract the 10 to the other side, leaving us with 1.5. So now if I divide both sides by 0.15 in order to get the Q by itself, I'm going to get Q equals 10. We have 10 quarters here. So let's go ahead and plug this back in to figure out how many dimes we have. D equals 100 minus our Q, or D equals 90. And so this is telling me I have 90 dimes in 10 quarters. Now our last step of any word problem should be to take a look at this answer and say, did I answer the question and does it make sense? So let's go back to the question itself, where the question itself said find the number of each type of coin. We definitely did that. So now let's see if this answer makes sense. We were supposed to have a total of 100 coins. Do I have 100 coins? Well, sure, I got 100 coins, 90 and 10. Now my value is supposed to be 1150. This should be pretty easy. If you got 90 dimes, that's $9. If you have 10 quarters, that's $2.50. Add those together, that's $11.50. That is what we wanted. So we can be pretty confident in our answer of 90 dimes and 10 quarters. Make sure that we're rereading the question and making sure that we're answering it too. We don't want to say something like D equals 90, Q equals 10, because we made up D, we made up Q. We want to answer in words and say, hey, there's 90 dimes and 10 quarters. Next example I want to look at is going to be a mixture problem. Now, mixture problems come up in a lot of different ways, but they all boil down to the same thing, that we're mixing two different things together to obtain a third thing. So in this particular case, we've got a candy store, and we've got these M&Ms that are worth $2 a pound. We've got some trail mix worth $1.50 a pound, and we're going to mix them together, stir them all up, and call this stuff party mix, and we're going to charge $1.80 per pound. So in this case, we're being asked how many pounds of the M&Ms and trail mix should I be mixing together so that the correct amount to charge for the 50 pounds is $1.80 per pound. So let's first of all organize the information of what's going on. And then let's try to stop doing any math and just take a common sense approach of what's going on. So I always draw mixture problems the same way. I'm going to take a bin plus a bin equals a bin. And I'm going to throw some information into these bins. Now inside the bin, I'm going to put the concentration. That's what's always going to happen in these problems, is there's a concentration involved. So in here, I'm mixing M&Ms with trail mix to get party mix. And the concentration of the M&Ms is $2 per pound. Now, sometimes concentration is given in percent. Sometimes it's per pound. There's always going to be a per in there when talking about the concentration. The trail mix was $1.50 per pound. And the party mix, $1.80 per pound. Now we do know that there are 50 pounds of the party mix, and underneath is where I'm going to put the amount of whatever it is that we have. So this is all the information that was given to us, and I want to talk about a common sense approach of how we're going to approach this from a common sense perspective. And what I always like to do for the common sense approach is to say, what if, and don't write this down over in our actual work, what if it was 25 pounds and 25 pounds? What if I just mixed equal portions of each? So if I had some stuff worth $2 a pound and some stuff worth $1.50 per pound, and I mixed them together, equal amounts, how much would I charge? Now, some people would say add them together and make it $3.50. Now, that's ridiculous if we think about it, because neither one of them is worth $3.50. The most expensive thing we're putting into this mix is $2 per pound. So we know we can't be more valuable than $2 per pound. The cheapest thing we're adding into the mix is $1.50 a pound. So we know that we're not going to charge less than $1.50 a pound. That wouldn't make sense. What makes sense if we do equal portions of each is that if we did equal portions, it would be the average. If we had equal portions of 25 pounds and 25 pounds, then we would charge $1.75 per pound, right in the middle. Now, we don't actually want to charge $1.75 a pound. We want to charge $1.80 per pound. So we got to say, all right, well, if I need to have a little more value to this mixture, do I want more of the cheap stuff or do I want more of the expensive stuff? And if we want to raise the price of it, we want more of the expensive stuff. So if we're looking at charging $1.80 per pound, then we better have more M&Ms. M&Ms are worth more. So that's going to raise the price that we can charge if we include more of the expensive stuff. So instead of a 25-25 split, we're expecting a little more like maybe 30-20 or maybe like 28-22, something like that. We're expecting a little bit more of the M&Ms than we are of trail mix. So again, some of the things that we pointed out, you might want to jot these down off to the side somewhere in your notes, is before we even looked over to the right-hand side of what we want to charge, we know that we're never going to be more valuable than $2 a pound, because that's our most expensive thing, and we'll never be less valuable than $1.50 per pound. That's how these mixture problems work, is the end results can be somewhere in between the concentrations. We know that if we did equal parts of each, it's the exact average. Now this problem is not the exact average, it's a little more valuable, so we're going to have more of the valuable stuff. All right, so now let's get to actually solving it. We need some variables. We need to figure out how much M&Ms and how much trail mix should be added together. Now we could use two separate variables if you really wanted to. I don't really want to, so don't write this down. I'm just going to point it out. We're going to eventually be able to approach this with common sense because this was actually a problem from our prerequisite course. So if I don't know how much, well, I know if I have X pounds of M&Ms and I have Y pounds of trail mix, if I add them together, I need to get 50 pounds. So what is Y really? Y is 50 minus X. So instead of actually using a Y over here, oops, I'm going to erase that. Instead of using a Y, let's just use 50 minus X. That way we don't even have two variables. We only have one variable. And this should make sense if we start throwing some numbers into there. If I had 20 pounds of M&Ms, I would need 30 pounds of party mix. How'd I come up with 30? I did 50 minus 20. If I had 40 pounds of M&Ms, I would need 10 pounds of trail mix. And again, that comes from 50 minus the 40. So 50 minus X gets us how much trail mix we need. Now to turn this into an equation, the way that this works is we multiply those two values, multiply those two values, and multiply those two values, and we keep the mathematical symbols that were already there. Now the reason that's how this works is because if I have 25 pounds of M&Ms at $2 per pound, I'm going to multiply those two things together, and that's how much money worth of M&Ms exists in this mixture. If I multiply the 150 times 50 minus X, that gets me how much total money's worth of trail mix I have. And if I add those together, it better be the amount of money worth of party mix that I have. And if we look at what's going on here, we now have one equation, one unknown. This should be pretty easy to solve. So 1.5 times 50 is going to get me 75. Distribute the 1.5 over to the X. And 1.8 times 50 is going to get me 90. I can combine like terms on the left with the 2x minus 1.5x. That's going to get me 0.5x. And I can subtract 75 to the other side. That's going to get me 15. And if I divide by 0.5, I'm going to get x equals 30. Now that I have an algebraic answer, I need to go back to my original problem and figure out how to answer the question and to see if it makes sense. The question asks, how much of each do we have? So it's asking how many pounds of M&Ms and how many pounds of trail mix. Now remember that we defined x as the number of pounds of M&Ms. So we can say 30 pounds of M&Ms. And then if we come back to our problem, for trail mix, it was 50 minus x. 50 minus 30 would be 20 pounds of trail mix. Now to make sure this answer makes sense, we do have a total of 50 pounds, and going back to our common sense approach, this was actually one of our guesses. We said maybe 30, 20, maybe, I don't know, 28, 22, but this was actually one of our guesses. So it makes perfect sense because we already got this through a common sense approach. All right, so let's do an example that involves some distance, rates, and times. Now, I didn't give an example of our typical train problem that everybody likes to groan at, but we might see some of those. Now, the thing with those problems is it sounds like a lot of information being thrown at you. And the key to these types of problems is really to dissect that information and figure out what it is you're looking for and figure out how things are related to each other. So the understanding and organizing the information is the most important thing to start off with. And so what we need to make sure we do is draw a picture so we understand what things look like, and then make sure we very carefully define each of the quantities involved in the problem. Not just defining our variables, but oftentimes there's going to be quantities that are given to us that are either a number that's straight up given to us, or it's somehow related to another quantity in the problem. So let's read this one. We've got these two cyclists that start at the same point and travel in opposite directions. One travels 4 miles per hour faster than the other, and in 4 hours they're 112 miles apart. Find how fast each is traveling. So before I start trying to define any variables at all, I want to draw a very rough sketch of what's going on. They're starting at the same point. They travel in opposite directions. And after 4 hours, they're 112 miles apart. Now, some important things to get out of this is we can first of all get a rough idea of how far each went. Now, we know that it's not exactly half because one's going faster than the other. So neither one of these are exactly 56. This isn't 56 miles and 56 miles. But that gives us a rough idea if we sort of say, all right, if they were going at the same speed, it would have been 56 miles and 56 miles. So as far as a rough estimate or a kind of a common sense approach, the one that was going faster is going to be more than 56 miles, and the other one is going to be less than 56 miles. Those should be our final answers. I'm doing this in blue so we know this isn't like an exact science that here. But this kind of gives us a rough idea of what's going on. Now, the other thing that we can do is we can apply similar reasoning to what we did in example 2. We know the total here is 112 miles. So if I knew the distance of the person on the right here is d, then I actually know the distance of the other one is going to be 112 minus d. It's the same idea that if I know the total between two things, I don't need two separate variables. I can just say, hey, if one of them is 70, the other is 112 minus the 70 that he is. So this is starting to get us an idea of what's going on. Now to start defining our quantities involved in this problem, we're going to create what we call a dirt box. Because we know that the underlying formula here is distance equals rate times time. So DRT with an equal sign in there is dirt, D-E-R-T. Math people can't spell. So we've got this dirt box that we're going to create. Now our rows are going to represent each of the cyclists. We're going to have the fast dude and the slow dude. And we're going to fill in as much information as we can. And we might not have every piece of information here, and that's fine too. So in this case, we know that the fast guy, according to our picture up there, his distance is d. The slow guy, according to our picture, is 112 minus d. Now, the rate that they're traveling at, don't know. Don't know the fast guy. Don't know the slow guy. Do know how they're related. The fast one is going 4 miles per hour faster than the other. So I need to call one of these guys x. Doesn't matter which one. You can call R if you want. Now the fast guy, don't write this down. One of the common errors that I see here is I see people say, oh, he's 4 miles per hour faster, that's 4x. But remember what that operation is between the 4 and the x? That's multiplication. That would be 4 times it. That's quadruple. That's not the same thing. If we're 4 miles per hour faster, that's an additive function. That's x plus 4. Now I do want to point out that this is not the only way to set this problem up. Somebody else might look at this problem and say, let's let the fast guy be x. If he's 4 miles per hour faster than the slow guy's 4 miles per hour slower. So I could call this x minus 4. Okay? Doesn't matter which way you set this up. As long as you jot down at the very beginning where we're at right now, we need to make sure that we jot down how we're defining our variables. That way, whenever I solve x equals, I can come back and actually answer the question. Now, as far as time is concerned, they both went for 4 hours. There was no head start or anything, so their time is 4. All right. So now we have 2 equations, 2 unknowns. Now we can solve it that way by actually having 2 equations, 2 unknowns. I want to talk about an alternate approach we could take to this. So we could look at this and say d equals 4 times x plus 4 as one equation, and 112 minus d equals 4 times x as my second equation, and I could solve this system. That's one approach that we can take to this problem. Another approach that we could take is we could say, if I take the distance of the fast person and add the distance of the slow person, if I add those together, I get 112. The distance of the fast person is going to be their rate times their time. The distance of the slow person is going to be their rate times their time. And the cool thing about this approach is that this only has one variable in it. So I could go ahead and distribute, then combine like terms, and I may as well subtract the 16 to the other side, and then divide by 8. Now we could go ahead and do that over here as well, and what we can see is that we're going to end up doing something very similar, which is a little bit more moving around. If I distribute the 4, I could then use substitution to plug it in over here. 112 minus 4x plus 16. Oops, hold on. 4x plus 16 equals 4x. I could distribute the negative. I could combine like terms and add the 4x to the other side. I'm going to end up getting the same answer with a system of equations. I just want to point out that there's 2 different ways you could kind of look at this problem and come up with the same answer. Now, please note that we haven't answered the actual question yet. We've only solved the algebraic part. Let's come back and read what we were actually asked. We were asked to find how fast each is traveling. So that's our rate. X, no, is the speed of the slow person. So when we got x equals 12 miles per hour for the slower cyclists, whereas the faster cyclist, their rate was x plus 4. So that's 16 if we add 4 to our x value. So for the faster person, they were going 16 miles per hour. Now don't forget to look at this and say, does my answer make sense? So in this problem, what I'd be looking at to see if it makes sense as far as their speed is to say, are these reasonable bicycling speeds? And so it's a good idea to have some general ideas of what speeds make sense in your head. So knowing that, for instance, somebody jogs at about 5 miles an hour. Knowing that you drive through a neighborhood at about 25 miles per hour. So keeping in mind things like that allows you to compare this and say, these people are cycling somewhere in between a jog and a drive in a neighborhood. Another way you can make some sense out of this is to come back to our picture and say, they traveled a total of, well, I'll let that one. We can look at the roughly half of this and say in 4 hours, if they went 56 miles, which they didn't, in 4 hours, then that would be about 14 miles per hour. And we know that one of them went faster and one went slower. So if we look back to this and say, oh, one did go 2 miles per hour faster and one went 2 miles per hour slower than that average there, that's a pretty good estimation or guess. So the answer does definitely make sense. Now the other thing I want to touch on that I talked about, but just to reiterate, make sure to reread the question because notice in this problem we had a variable for distance. We never solved for it. We weren't asked about it. And that's okay. Now if you want to solve for it, you could. You very well could figure out what the distances were that we could say, all right, well, coming back over here, at 16 miles per hour for 4 hours, the faster guy went 64 miles. Well, that fits into my a little more than 56 miles idea from the beginning. So even though we weren't asked for it, you could solve for it. But again, make sure you reread the question and solve what you're actually being asked for. All right, the next topic that we're going to talk about is going to be either one of two situations. Boats that are traveling in a current or planes that are traveling in a wind. And both of these physical situations are going to basically behave the same way. So I want to make sure that we understand how they behave so we can start to identify where should we put our variables and how should we define our variables. And I can't stress this enough. We need to define our variables in words at the beginning of the problem. I see this semester after semester, people not defining their variables in these problems and getting them wrong because they don't remember what they're even solving for. So it's really important to define in words what we're trying to do in these problems. So let's first of all understand what's going on when we're paddling in a canoe, in a kayak, in a river. So let's go ahead and kind of draw a picture of what's going on here. So we have, here's my beautiful version of a river. And let's go ahead and say the current is going in that direction. And let's go ahead and make a different color. Let's go ahead and do yellow and say, I'm paddling in that direction as well. So what I want you to picture is you're paddling with the current. So what if there was no current at all and you were just in a still pond? You could paddle in one direction at a certain speed. Now, if that current starts to push you, you're going to actually go faster. Whereas if you're trying to fight the current, if you're going against the current, you're going to go slower. So to throw some numbers in here, let's say you're trying to paddle at 4 miles per hour, we'll say. If you're paddling at 4 miles per hour in still water, and there's a 2 mile per hour current that pushes you, how fast do you think you're actually going? If someone's looking at you from the shore, you're actually going 6 miles per hour. Now, what if you go all the way upstream or downstream rather, and you decide to stop and have lunch, and then you want to head back to where you'd parked your car at? So all of a sudden, you have to start, well, actually, I guess the river stays the same direction. So let me go like that. And let's say that you want to start traveling the opposite direction. So you want to fight the current. If you were fighting the current, where you're trying to paddle at 4 miles per hour, but you're fighting a 2 mile per hour current, how fast are you actually going? 2 miles per hour. So in general, what's happening when you're trying to fight the current or going with the current is when you're going with the current, you're going to take your speed in still water plus the speed of the current. And that's the speed that you're actually going. Is you're going to take the speed that you're trying to go in still water, add that to the speed of the current, and that's how fast you're actually going. When you go against the current, you're going to take your speed in still water, the speed you're trying to go, and you're going to subtract the speed of the current. Now, the order of subtraction here matters. You're going to take the speed of the current off of your speed, which hopefully makes sense. If you try to flip-flop that, you're going to end up with a negative number, and that doesn't make sense at all, because you're always going to have to be traveling faster than the current in order to make progress. Now, I wanted to write this out in words and not throw letters and variables into the mix, because you need to understand physically what's going on. Now, this also tells us, though, what the variables are that we want to define in any of these problems. We're probably going to define one of our variables to be your speed in still water, unless it's given to us. The other variable is probably going to be the speed of the current, unless that value is given to us. But these are the quantities involved in the problem, and this is the physics of how it works. You need to make sure that you understand this in order to be able to set the problems up that utilize it. Now, I mentioned earlier, this same thing applies if you're flying in a plane. That you can take the speed that you're trying to fly as though it was still air and add the speed of the wind when the wind is pushing you. When you're trying to fight the wind, you're going to subtract the speed of the wind. Now, in this class, we're going to assume that we're either going directly with the current, directly with the wind, or we're going directly against it, like head into it. Now, in a class beyond this, if you take a trigonometry class, you can start to explore what happens if the current's hitting you at an angle, or if the wind is hitting you at an angle. It's going to knock you off course a little bit, but it also might speed you up or slow you down depending on which direction it's coming in. But for this class, this is what you need to know, is that when you're going with the wind or the current, you're going to take your speed in still water or still air and add the speed of the current or the wind. And when you're against, you're going to subtract the speed of the current or the wind. So in this example, we've got the Smith family that took a canoe 10 miles down the Au Sable River, and it took them 1.25 hours. They had some lunch, and then it took them 4 hours to return. And we're supposed to find the rate of the current. So let's kind of see what's going on here. So we're starting at some location here. We're going to go for, it says 10 miles. And then we're going to have lunch here. Those 10 miles took us 1.25 hours. Now, after lunch, we're going to go back to where we started from. It's going to take us 4 hours. Now, in looking at this picture, the distance didn't change. The distance is 10 miles in each case. So the distance doesn't change, just the time. And the time makes sense that you're going downriver, you're going fast. If you got to fight the current the whole way back, you're going to be really tired and it's going to take a long time. Now let's try to organize our information in a dirt box. So we got D equals R times T. And we need to organize each of these quantities that are involved. Now in this case, our two rows are going to be with the current and against the current. Now, as we said, in each way, the distance stayed the same. The distance was 10 miles. The time is straight up given to us. So these are numbers that we can just plug in. So with the current, it took us 1.25 hours. Against the current, it took us 4 hours. Now let's talk about the rate. So as we talked about in the intro to this example, we know that when you're going with the current, your speed is your speed in still water in this case, plus the speed of the current. And when you're going against, then you're going to take your speed in still water minus the speed of the current. Please write this out in words. It's really going to help you understand what's going on in your problem and not just throwing variables in there. Now we can see what our variables need to be. One of our variables needs to be our speed in still water. So the speed that we're trying to paddle if there was no current at all. And y can be the speed of the current. Again, writing this out in words. And what this tells us is our speed when we're going with the current is x plus y, and against the current our speed is x minus y. And this then gives us two equations. 10 equals 1.25 times x plus y, and 10 equals 4 times x minus y. We need to solve this system of linear equations in order to get our answer. Now, here's the nifty thing. We don't actually need to solve the entire system. We're being asked to find the rate of the current. That's our y value. We're really just being asked what's y. So as I come back to this problem and I want to solve it, the first thing that I would look at is to say, if I could ignore those pieces there, this problem would be really easy to solve by the addition method. Now I can't just get rid of them, but what I could do is divide both sides by 1.25, divide both sides of the second equation by 4. In doing so, let me get my calculator out just to make sure. Pretty sure I can do these ones in my head, but I don't like to make mistakes, especially when I'm recording a video. So we're going to go ahead and do 10 divided by 1.25. And that gets us 8 for this guy. We're left with the x plus y. Now for the divide by 4 piece, we have 10 divided by 4 gets us 2.5. And that leaves us with just the x minus y. Now we could go ahead and use the addition method right here, but what variable would that eliminate? The y's. And what variable am I trying to find? The y. So let's not eliminate the y's, let's eliminate the x's. So let's multiply this guy by -1, and if you saw ahead one step at that, you could have just divided by -4 in the first place rather than +4, but that's all right. That's going to get us -2.5 there. We're going to get -x and +y now. So when I use the addition method, I'm going to get 5.5 equals x minus x is 0, but y plus y is 2y. Don't forget that this is the addition method. I get a lot of people that forget the 2 here. They forget that we're saying y plus y. So now to solve for y, we divide both sides by 2, and we get 2.75 equals y. If we come back up to the original question, the question was find the rate of the current. Our answer for y does answer that question. So 2.75 miles per hour is the speed of the current. And then to think about whether that answer makes sense or not, we can think about the fact that paddling a boat is similar to a walk or a jog to the point that 5 miles an hour makes sense. The current needs to be less than that because we're going to be able to fight against it. So this answer does make sense, that we have a current of 2.75 miles per hour. Now we will also have some word problems that lead to systems of 3 equations, 3 unknowns. And that's okay, that happens. As we read through this, we can see that there's a whole lot of translating stuff going on. But basically what we're looking for is the digits of a 3-digit number. So as I'm trying to define my variables of x, y, and z, I'm going to define them as these digits, where x I'm going to define as the hundreds digit. I'm going to define y as the tens digit. And I'm going to define z as my ones digit. Then I'm going to go through each sentence, where the first one says the sum of the digits is 15. So that's pretty easy to translate as x plus y plus z equals 15. Now, as I go to translate the second sentence, we're really just going to be looking for our normal keywords. The tens place digit, well, that's y. Is means equals. Twice the hundreds place digit, 2x. Then I read the next sentence. The ones place digit, that's z, that's equals 1 less than the hundreds place digit, x minus 1. Now this particular problem is really simple to solve because of the fact that we have a y equals and a z equals, and both of those are in terms of x. So this would actually be a really easy problem for substitution by saying I can substitute both of these into the first to get x plus, then instead of y putting 2x, instead of z putting x minus 1 equals 15. Now I'm not actually going to do that because I want to show you how we're going to do most of these systems that have 3 equations, 3 unknowns. That way you're prepared for anything, not just this special case. What I would suggest doing if I were you in this system of 3 equations, 3 unknowns, is to make this look more like the ones that we're familiar with from our homework. So when we dealt with all of our 3 equation, 3 unknown systems before, all the x's were lined up, all the y's were lined up, all the z's were lined up, and the numerical value is on the other side. So I would rewrite it in that way. So the first equation was already set up that way. But the second equation, the blue one, I would subtract the 2x over to the left. That leaves me a 0 on the right, and there were no z's in that one, so we're just going to leave the z one blank. Then for the third equation, the red one, I would subtract the x to the other side, giving me negative x plus z equals negative 1. So I would look at my system in this way, and that way I can solve it just like I did any other 3 equation, 3 unknown system, where I would start off deciding which variable to eliminate, and I would probably choose either z or y, doesn't really matter which one, but we're going to make sure to make that note of which one we do. I say I'm going to eliminate the z's. That means I'm going to copy down the equation that doesn't have a z in it already. And then I'm going to go ahead and multiply this third equation by negative 1. That way off to the side in my scrap paper land, I copy down the first equation, and then I multiply by negative 1 for the other equation, and then add them together. And I get 2x plus y equals 16. I copy that down over here. And now this system of 2 equations, 2 unknowns is really easy to solve because the x's are ready for the elimination already. So if we add them together, we get 2y equals 16, or y equals 8. We can then take this value of y equals 8 and plug it back in to figure out our value of x. So 2x plus 8 equals 16. So 2x equals 8, or x equals 4. And now we just need to figure out our z, which we could actually do pretty easily by plugging it in there. Because I could get negative x plus z equals negative 1. Add the 4 to the other side gets me 3. Now if we go back to the actual question in this case, the question was, find the 3-digit number where x was my hundreds place, y was my tens, and z was my ones. So that tells me the number here is 483. That's going to actually answer the question in this case, since we were asked what the number was, even though we solved for each digit independently. Now, as far as whether our answer makes sense in this problem or not, it makes sense because each of those digits were actually a digit. If we would have got negative numbers or decimals, we'd say, oh, hold on a second, this is weird. Even if we got a 2-digit number, if one of these was 20, that wouldn't make sense. X, Y, and Z were each a digit, meaning they were either going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. We did get those values, since that does make sense, and this is our correct answer.